Okay, Engel and Reid, problem 12.7. This is from a homework assignment. Show that the energy density, sorry about that, radiated by a black body, which is given by this, E per V, that's the energy per unit volume, is given by the integral rho d nu, which is equal to the integral 8 pi 8 h nu cubed over C3 1 over E h nu over kt minus 1 d nu. That's what it's given by, okay? So we're supposed to show that this energy density, that is the energy per unit volume, radiated by a black body, depends on the temperature as T to the fourth. And then we're given this hint, all right? Well, this hint is really, the hint is x, make this substitution x. This is like u substitution, except, this is not dx, it's d nu. So we're just going to use x. It's equal to h nu over kt, which is that right there, right? Let's see. And then the definite integral, this is another major hint. The definite integral x to the third over e to the x minus 1 dx is equal to such and such, right? Pi to the fourth over 15. Major hint. So basically what it's saying is, use this right here, use this substitution, and try to get it into this form. And, try to get the integral in that form. I see it as a very, if all I have to do is obey this and then see what happens, right? I think it's going to make it so that the question isn't, ends up not even being, it's going to fall out for me, so long as I, take care of my math, okay? So, alright, so the energy density is given by this integral right here. First thing I'm going to do when I'm doing integrals is I'm going to take all the constants and move them outside the integral to make this look cleaner. There's just a lot of junk in here, right? So this is the integral with respect to nu. And so that is a constant with respect to nu. That's a constant with respect to nu. That's a constant. Well, these are all constants anyway, even not with respect to nu, right? So look at all that stuff. I can bring that outside the integral. So this is the same thing as 8 pi h over c cubed, 0 to nu cubed, 1 over e h nu over kt minus 1 d nu. Right? All I've done is change the form of that. I haven't done any math at all. But I'm getting ready to do some here, right? Because I'm going to take these two hints, major hints, and see what to do with them. All right, so if I'm going to do a substitution of that and that, right, I can see that that is my x, is like boom. Okay, and look at that. Okay, so let's go ahead and do that right now. If x is equal to h nu over kt, then x kt over h is equal to nu. Dx, or rather d nu, is going to equal dx kt over h. Okay? And I've got that nu cubed, right? So nu cubed is equal to x kt over h all cubed, which is equal to x cubed kt over h cubed. I'm doing that because I'm trying to get it into this form here. So I'm sort of funneling it in that direction. All right, now that I've got that, I'm going to bring this down here and say this is equal to 8 pi h c3. Okay? Now, first of all, nu cubed. I'm bringing it down here, right? Nu cubed is x cubed kt over h cubed. I've replaced now my nu cubed, right? And now I'm going to replace that with x, because that's what x was. 1 over e to the x minus 1. And then d nu. What was d nu? D nu was dx kth, all right? Dx kt over h. These are constants again, right? So it looks like it's kt over h to the fourth. And those are all constants, so I'm going to bring those out. This is equal to 8 pi h c kt over h to the fourth. Agreed? I bring that out, and all of a sudden, boom. I'm now in the form. This is the other hint I was given, right? I'm going to get rid of one of these h's. See, there's an h here, and there's 4 h's down here. So I'm going to say pi over c 3h3, right? Across one of them off. K to the fourth, t to the fourth. Okay, and then this becomes pi to the fourth over 15. All right, so there's my answer. It's 8 pi to the fifth, because I got that too right there, right? C3H3 15. Boom, 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 boom. K to the fourth times t to the fourth. But that was my whole goal in the beginning, was show that the energy density depends on the temperature as t to the fourth. And that's what I got. That is, the energy density is a function of temperature to the fourth. Okay, so QED, that which was to have been demonstrated. Quod erat demonstrandum, I think, is what that stands for. Alright, so hopefully that's helpful. I think the next part of the question is, using your results, calculate the energy density radiated by a black body at 11,000, or rather 1100 and 6,000 K. And, you know, I think I don't have the energy to do that right now. I'm going to leave that off this video. You see what I'm going to do. I'm just going to take 8, pi is a constant, K is a constant, that's Boltzmann's constant, 15 is a constant, it's 15, C is a constant, it's the speed of light, and this is Planck's constant, which is 6.626 times 10 to the negative 34. So these are all constants. All I got to do is find out what that number is, and then multiply, or rather take temperature at 1100 kelvins, multiply it times 1100 raised to the fourth, and that's going to be the energy density at 1100, and then multiply it. Take that same number and multiply it times 6,000 raised to the fourth, and it's going to be the energy density. Hopefully that's helpful. If not, please let me know.